Morning, Curie and fellow contestants. Today, I'm the reporter from Team Taiwan, and we're going to be discussing our problem number 12, three-point engine. So let's take a look at my presentation outline first. So firstly, I will be introducing the topic, and then we will be introducing our theory. And we'll have two parts in our experiment. First part is inspecting the relevant parameters, and the second part is actually concerning optimization of this three-point engine. And we'll finally end at our conclusion. So our introduction first. Let's take a look at the problem statement. The problem statement tells us to make a nickel disc that rotates freely around its axis. Place a magnet near the edge of the disc and heat the side of it. The disc starts to rotate. Investigate the parameters affecting the rotation and optimize the design for a steady motion. So firstly, what are some possible parameters that will affect the rotation of this nickel disc? You can see that these are some possible parameters including the position of the heating, the efficiency of our heating device, and also some parameters of the disc. And secondly, what is the definition of the steady motion that is actually in the problem statement? There are two levels of steady as concerned by the reporter. So the steady motion should be a continuous motion, and it also should have a constant angular velocity, so we will be investigating on that. So this is our observation video. As we can see, in our initial observation, as the nickel disc actually rotates, it's actually not quite continuous, but rather choppy in some ways. Now, when we graph the rotation angle and its angular velocity with time, you can see that this black line is the rotation angle, and the red line is its angular velocity. The angular velocity at first is almost always zero, but there are peaks in its angular velocity, indicating that there are actually jumps in the rotation. So let's come to our theory part. The final coordinates we'll be using in our presentation. So this is our magnet that is placed on the x-axis of this disc. The h is the coordinates of the center of the heating area in respect to this disc. And then we have the radius of the disc and the thickness of the disc. Now, we would like to introduce the saturation magnetization of nickel plotted against temperature. So as we know, nickel is a ferromagnetic material. And originally, under room temperature, it had a saturation magnetization here. But as we heat it up, because the magnetic dipoles inside get realigned, so the actual saturation magnetization will drop because of the temperature rise. And we can see that this drop is actually not linear, but the drop gets higher when it approaches near the Curie point of nickel, which is 627 Kelvin. And a theoretical approach we would like to use for this problem would be, we can simplify this. We can first see two symmetrical sides of this nickel disc. And then here is a magnetic moment that is a function of its time and its distance to the actual magnet. And it's under a magnetic field of B. And then when we have this field and this magnetic moment, we can get the actual energy of this part through the interaction energy of a dipole in the magnetic field, which is U equals negative mu dot B. And then we can get the magnetic force using the actual energy. So these components on the x direction and the y direction can be noted like this. Now once we get the force on these two directions, we actually have to do a correction, because when the actual temperature is under the Curie point temperature, the absolute value of this magnetic moment would be approximately its saturation magnetization. But concerning, we have an actual angle between the two vectors of the magnetic moment and the actual magnetic field. We have to assume that the direction that is parallel to the magnetic field is proportional to the magnetic field itself with a factor of t. And then we can get the actual correction of this magnetic force on the x direction. Therefore, we can get the torque that causes direction by the net torque that causes direction would be the two forces times its arm of force and then subtracting each from each other. So this would be the torque that is caused by the magnet, and this has to be larger than the torque caused by resistance in order for the nickel disc to actually start to rotate. Now, a qualitative explanation to image how this actual phenomenon happens. So firstly, as we put a fire under this heating spot, you can see that the actual magnetic moment decreases because of the heat. Therefore, this magnetic force will also decrease, causing a rotation. Now, we actually know that there isn't only temperature increase in this actual heated area, but actually there is a temperature gradient on the plate. So all forces that are actually all locations on this plate that have experienced a pressure in temperature increase will actually have a change in the magnetic force. So our first experiment would be about the relevant parameters about this Curie engine. So let's take a look at our device first. We have a rotation axis at the top of the nickel disc, and we have nickel discs of different radiuses and different thicknesses. So this is our experimental device. And then we put this Curie engine above the heat source, and then we put a magnet beside it to let it rotate. And this is what it looks like from the top. So firstly, you have to investigate the previous image we saw earlier. So this is the rotation angle versus time, and this is the angular velocity versus time. You can also see in here that initially the actual angular velocity is approximately 0 at many times, but there are peaks in its rotation. So because we can't see the motion isn't continuous, so we use the percentage of the time that the angular velocity equals 0 to evaluate its actual continuity. And also because this is actually a Curie engine, therefore a very important indicator of an engine is its thermal efficiency. Therefore, we will use its rotational kinetic energy over its energy input to evaluate actually how good the thermal efficiency is for this engine. So a qualitative explanation on why the actual rotation of the Curie engine is not continuous. So we can see that firstly, there is no rotation here because the actual temperature of the heating spot hasn't exceeded the critical point to let the actual torque caused by the magnet increase higher than the torque caused by the resistance. Therefore, there would be no rotation here. Once it exceeds this critical point, it will begin to rotate. And when it actually suddenly rotates quick enough, the next spot that is heated will not have enough temperature to go above the critical point. Therefore, it requires a reheat, as we can see here. It goes back to the stage that is not rotating anymore. And then we can see that the slope in this actual rotation phase changes with time. And this is because the actual magnetic moment to temperature function, as we saw in the previous slides, is not actually a linear proportion. So it actually changes more when it has a higher temperature. And then we try to change a different heating spot. We put the actual burner under the nickel disc. And we can see here, this is the actual theta T graph you can see. So we can notice here that the most continuous rotation as seen from this graph is not actually the nearest spot nor the further spot to the magnet as shown here, but it actually somewhere in between. So we evaluate its continuity as we talked about earlier. We can see that the most continuous motion comes from when the burner is put about 1 centimeter to the edge of the disc and at about a 30-degree angle to the x-axis, which is the axis of the magnet. And when we actually put the alcohol burner into a deeper part inside the nickel disc, it doesn't rotate as well as seen here. So we evaluated the thermal efficiency of the engine at different spots. We can see that this heating spot, which is the same heating spot for the most continuous motion, is also the most optimized for the thermal efficiency of this engine. And also, we did a 4 centimeter disc diameter, which we also put the heater at different positions under the disc. We can also see that there is a similar optimized heating spot. This blue dot, we can see this is also about 30 degrees to the actual. It's 30 degrees to the actual x-axis and about 1 centimeter to the actual border of the disc. Now with the different thicknesses of the disc, we can see that the thinner disc has a more continuous rotation. And this is probably this would be because of the moment of inertia of the disc and also the thermal conductivity of the disc. Now with the different heat sources, so we put a Bunsen burner instead of our alcohol burner, and we can see that we use a thermal scanner to scan this result. We can find that for the alcohol burner case, in the initial part of the rotation, there is only regional temperature increase. Therefore, there will be a large time difference between rotations. And then at the more later parts of the rotation, there will be a more continuous temperature gradient. Therefore, we can see the slope here will be more smooth. And then if we use a Bunsen burner, there will be less time required to reach desired temperature between motions. However, when the whole disc overheats, there will be no rotation anymore because the whole disc actually exceeds the Curie point. And then we can't see any significant magnetization difference. So these are some directions of optimization we would like to do. And then the next part would be about how we optimize our device. So we use our optimization step. We put the Curie point engine vertical, and then we put a water tank underneath it. And then we recorded the temperature of the heating spot using this infrared infrared thermometer, sorry. And then we graphed its temperature versus its rotation. And then we can see that when there is a sudden jump in the angle, we can experience a decrease in the temperature of the heating spot. So that actually verifies my previous explanation when I said that when there is a jump in the angle, the next heating spot is not heated to a high enough temperature. And we can see the initiation of its rotation is at 164 degrees. The first jump is at 257 degrees, which is both lower than the Curie point. So our actual Curie point engine rotates under the Curie point. And then we investigated different temperatures of the water tank under it and its continuity. We can see that appropriate cooling can improve continuum percentage, so it's not necessarily lower temperature of the water tank that will have a better continuity. And also we can see when we put a 48-degree cold reservoir, it also has a less deviation of angular velocity, indicating that it rotates more steady. And finally, we'll optimize the device by drilling holes in it symmetrically. And we can see when it has actual holes in it, its continuity can reach 100% of its rotational time. And that its angular velocity is also significantly higher than the one with no holes. So in conclusion, the mechanism of rotation would be the temperature difference induced mapping the force difference causing a cold cloud click. And we investigate some parameters affecting rotation, including position of the heating, diameter, thickness, and efficiency of the heater. We also optimize the design for a steady motion by adding a water tank to improve the temperature gradient and cool the whole system down. And also we reduce the mass of the disk by drilling holes in it to actually achieve a more continuous rotation. So in our optimization, we can actually reach a continuous rotation throughout our experiments. So this is the end of my report. Thank you.
So I would like to ask some short questions to Mr. Reporter. So first, can you use the saturization magnetization in these cases? Yes or no question?
It is not.
Please answer yes or no, please.
Partially.
Partially. And did you consider the heat conductance from the heating point you considered?
Yes, so we said that there will be a temperature gradient.
And how did you consider the friction in these cases?
Yes, we did. That is the resistance here.
Yes. And then, do you think that engine's thermal efficiency is the important parameter in this problem?
It is a point of evaluation of this engine.
Okay, thank you. And do you think so this is the short answer, please. So what was the temperature of the heating source's flame?
What about the temperature?
So what was the temperature of the heating source's flame itself?
We
have used the alcohol burner,
yes.
And how was the temperature?
We didn't actually measure the temperature of the flame, we just only measured the temperature of the
Okay, I see. So if we change the alcohol burner into the more powerful heating sources, then do you think that your theoretical model does not apply to those kind of situations?
We actually
still applies?
We actually changed it to the more efficient burner, the Bunsen burner, and we can actually see.
You have changed it into the Bunsen burner?
Yes, yes, yes.
Well, then what was the maximum temperature that it reached when you used the Bunsen burner? The temperature of the disk.
We can observe that the disk actually becomes piping hot, so we actually know it's
maximum temperature was
it's way over the Curie point, maybe about
way over
60,
the Curie point. Okay,
600.
So the next question is, you have changed the nickel disk size in your experiments.
Yes.
So at what extent you could change the disk size? So from what number to from what number? Minimum size to the maximum size.
We only did two sizes, 4 centimeters radius and 5 centimeters.
Okay. So if you change the in your case, you have changed the vertical situation and horizontal situation at a specific time. Hello, ladies and gentlemen, and honorable viewers. I'm from Korea, who would like to deliver the opposition speech against the problem number 12, 3.10. So, this is the summary of their presentation. So, they have stated the problem, and after that, they have utilized the saturation magnetization value, and after that, the torque related to the conditions for rotation have been utilized, and the qualitative explanation of the rotation also have been delivered. After that, they have delivered about the experimental progression into two parts. First part was about the relevant parameters, about the experimental apparatus, and the qualitative explanation for non-continuous rotation have been delivered also, and also the varying parameters such as hitting spot, or radius, or the stiffness have been also delivered. After that, the optimization have been delivered in these cases, so the qualitative explanation for optimization also delivered, and the qualitative observation of the optimization delivered, and extra methods optimization has been delivered, and also in the experimental progression, the heat efficiency part also has been included. So here is some strong and weak points of their presentation. Well, they have delivered, explained very nice model, and also they have shown very nice visualization. Also, they have well explained the assumptions, and the errors have been also considered qualitatively. Also, the understanding of the grid temperature and the cooling procedure was quite a nice point of their presentation. However, they misconsidered some parameters such as the axis and the magnet's position, and the theory such as in the theory part they have explained about the horizontal rotation, and the experimental part they have suggested about the vertical rotation, in the optimization part. So I believe that the dominant physics in the horizontal rotation and the vertical rotation is quite different. So I would like to elaborate on this part in the discussion. And also, the heating area as a spot as the consideration was the weak point of them. And also, the lack of the quantitative explanation is the problem of them. Also, they did not show any calculation or the measurement of the friction is also the weak part of it. The thermal efficiency. They had considered the thermal efficiency of the Curie point engine as the evaluating their Curie point engine itself. So this is not the very big point, but they focus too much on to the thermal efficiency, which is not actually the problem asked. And then there was no theoretical optimization in their speech, so that is why they have delivered theoretical optimization was not possible in their cases. And also, the axis name and the error bar was back in their presentation. So here are some main discussion points that I would like to elaborate on in this discussion. So first one is about the magnetization saturation. They have utilized the magnetization saturation in these cases, and they have answered they can partially use it. However, I believe that magnetization saturation should not be used in this case. Rather, the magnetization remanence volume should be used. And also the heating source. They have answered that if whenever they change the heating source, the same physics actually is dominant. However, I believe that the regime, the physical regime, and also the heating area can be changed if they change the heating source. And also, the friction they have not considered about the theoretical model exactly about the friction, and I believe that in the vertical situation and the horizontal situation, this friction can be very resolved. So that's why I have to discuss in this part with the reporter. And here are some other discussion points, such as the optimization. They have suggested the optimization theoretically. However, I do not. They have not suggested this optimization theoretically, and also they have suggested the vertical part. And also the heat conductance is going to be discussed during the discussion, and also the intertwined parameters, such as when we change the disk size, and then other parameters can be changed, so this is going to be delivered. So I would like to invite Mr. Reporter to the podium from now on.
Okay, so firstly, can I explain how we actually calculated the friction? So
how did you calculate friction?
So,
yes, please.
So because we have two setups. One setup we actually put the actual plate in water. So we actually calculated the resistance from water. So we actually let it run and then measured its angular deceleration.
Okay, sir. Sorry, but did you consider the friction theoretically?
Yes. So we turn to the.
Okay, sir. I think it would be discussed when we discuss about this friction part. So first, I want to point out that this magnetization saturation should only be used when the H field is very strong, which means that in your case, how was the magnetic field strength in your experiment situation? Would you reply in the value, please? The maximum value?
2 milliteslas.
2 millitesla? Well, I do not know exactly, but did you check that it matches the minimum condition for the H field?
Okay, so can I explain on that? So turn back to the theoretical page. Okay, so you notice that we actually use a proportional factor key here. So we know that the magnetic moment would be not entirely magnetization, but we know that it will have a similar trend with the saturation magnetization when it drops to temperature.
Excuse me, sir. So you believe that it does not perfectly matching to the magnetization saturation in this case?
Yes. So we have a factor.
However, the tendency should be the similar.
Yes.
Well, okay, I partially agree on your point. And I would like to move on to the next point, which is about the heating source. So you have answered that even if you change the heating source, the physics, which actually the dominant is equal. Do you agree?
Yes. So
excuse me, sir. So I would like to ask you this point. So in my opinion, Mr. Reporter, if the heating source is changed into the Bunsen burner, and if the temperature is decreased to the more than 354 degrees Celsius, which is the Curie temperature, then it means that the regime which is dominant is changed into the paramagnetic situation, and you cannot use the magnetization saturation anymore, and you should apply the Curie-Weiss law in this situation, I believe. So in your presentation, it was not included, so please.
So we would like to know that when it actually goes over the Curie point temperature, it goes from paramagnetism into paramagnetism.
Yes, sir.
And then we can use this factor.
Paramagnetic susceptibility.
But we know that this factor is of a case of 10 to the power of -3 to this factor. So we consider that this force would not be big enough to actually initiate the actual rotation. So the rotation we observe is mostly under the Curie point. So that is why we observe this physics.
Mr. Reporter, I understand. However, if we this is the disk in your condition, and if we hit this part, and as you have replied to me, the heat conductance can make the other part as very high, near the Curie temperature. Do you agree? So in the magnetization saturation graph, it follows like this way, and then it gets to a very decreasing rate is very high if it is reaching to the Curie temperature. So I believe that if we have to consider these parts ferromagnetism as also zero, but since the lack of time, I think it would be better to move on to the next one.
So can I do one final?
Yes, sure.
So can you turn to page 27? So in our experiments, we actually see there is actually steady rotation around this point. I just want to say when we hold this is above this point, then I don't think there will be any rotation.
Okay, so you think it's not significant? Well, Mr. I think it is significant, but our opinion is not actually matching, so I think it would be better to move on to the next discussion point. So the next discussion point is about the friction. So this is the disk we consider, and this is the axis. So you put something here to fix the position. So fix the position of the disk itself.
Yes.
So did you consider this theoretically, this mu k, the kinetic friction coefficient in this case, to perfectly consider this friction theoretically? But this is yes or no question.
We just measured this friction, so we actually measured the entire.
So you have measured the entire friction.
Yes. So yeah, as we saw in the graph.
Yeah, like that you have shown me. So thank you. And then, was the friction has changed as the disk size changed?
So when I clarify my experimental step, so I actually have two nuts here, and then we have this other.
Yes, sir.
And so the actual thermal expansion of the disk might affect sometimes between the resistance inside. So yeah, that is a possible thing that.
However, I think it is quite not really considerable. It is quite negligible.
Yeah.
But I meant that is the friction differed very much, but you replied me that it is not differed much in your case.
Yes.
Okay, well I understand your reply. And next is about the optimization of the your Curie point tangent model. So you have suggested the experimental part, why it is optimized, and then you have explained this quite qualitatively why, but can you theoretically suggest the optimized omega, angular speed in these cases?
Okay, so we quantitatively explained that when you have a water tank under here, it provides the actual three-point engine for a better temperature gradient, so it rotates more smoothly. However, the actual effect of the water tank is not only that, but actually also damps the motion, so that it doesn't turn a lot for one rotation.
Okay, sir.
So
you did not calculate the optimized omega in this case.
Yeah, we did not actually calculate it in our theory. We just actually performed experiments.
So we cannot 100% sure that it is the optimized case because the number of experiments you have conducted is quite limited. So among the experiments it was optimized, but among all the cases it cannot be the optimized situation, isn't it?
Yes, so we actually try to approach, so our approach was to go to more and more continuous rotation.
So in the case of the optimization, so from the experience, there was no estimation of this kind of theoretical value. Well, there can be estimated in this case, so there was no estimation. Estimation of the theoretical value of the optimized omega.
Okay, can you explain all that? Because I don't know.
I'm really sorry, but I think it would be better to move on to the next one. Well, actually, it is not really significant point, so it was not really significant point. So next is about the heat conductance. So you have put the hole inside the disk, and then if you put the hole inside the disk, then there can be the difference in the heat conductance. So did you consider the heat conductance rate of the disk? How did you consider the heat conductance rate of the disk when you put the hole inside?
Okay, so in our experiments, as we see, when we have a hole inside the disk, we have a better continuity, and we said that it could be because of two reasons: the thermal conductance and also the actual moment of inertia of the disk. So the actual improvement in the optimization is caused by both things.
So I mean, did you theoretically or qualitatively consider this kind of heat conductance when you put the hole inside here? So I believe that if you put the hole inside here, the heat conductivity is better.
Because the actual, not that it would, what I mean is this. So when we actually have a disk with holes inside it, you can see that because when we heat it here, there's less mass to actually heat over here, so it will actually approach the desired temperature quickly.
Okay, it would approach to the desired temperature quickly, which means that the thermal conductivity actually decreases because this heat does not dissipates into the another part, and then since the thermal conductivity gets lower as the hole gets hardened, so that's why it is captured here. So do you agree on it?
I mistake when I talk about it.
So lastly, I would like to discuss about the intertwined parameters you have considered in the presentation. So first, when the disk size changes, I believe that if the disk size changes, the magnetic field also gotta be changed. And also, the position of the magnet should be considered differently. If we change the disk size, and also the effect of the flame should be considered differently, and also the heating rate and the cooling rate can be considered differently in this situation. So do you believe that if you change the disk size, then did you change the parameter only one parameter, or you can consider this parameter as the multiple parameters?
Okay, so actually when we compare the thing about the disk size, we compare the different heating spot on the same disk size, and our conclusion was that there is a similar optimizing angle here. So we didn't actually compare one disk size to another disk size because, as you said, there are multiple parameters changing when changing the disk size.
So actually, since the lack of time, I meant that when the disk is here and the magnet is here, and if this size is different, then the actually magnetic field acting on the disk should be different.
So we actually put it the same distance to the magnet, and then we.
Then the problem gets. Then the problem is more significant because if it changes, then the magnetic field.
Okay, happy. So we have 1 minute to come.
So today we had the discussion with the reporter about the Curie point engine, and there were several discussion points were evaluated. And also, firstly, we had considered about the magnetization saturation. Well, actually, reporter admitted that their theoretical model is not perfect, but they have answered that the tendency should be similar to the magnetization saturation graph. Well, actually, I partly agree, but I cannot totally agree on that point. And also, the heating source, they have answered that if they change the heating source, they have considered the paramagnetic susceptibility as negligible. Well, actually, I also partly agree on that point, but not perfectly. So, and also, the friction was discussed in the presentation, in the discussion, and also they have not considered friction theoretically. And also, in the case of the optimization, also the theoretical consideration of the optimization was not delivered properly. And also the heat conductance case. Well, actually they had made a mistake in this part, but it was not very significant. But they do not properly reply to this point, and also the parameters are considered. Thank you.
Hello, my name is Mansell. Today I'll be reviewing problem number 12, Curie point engine. So, reporter, did you ever get to a point where the angular velocity was constant? Yes or no?
Not entirely constant. There was always a standard deviation.
Reporter, did you vary anything about the magnets? Yes or no?
No, we did not vary the magnets.
Thank you. Opponent, is testing only 2 disk sizes sufficient?
Yes or no question?
Yes or no?
No.
Okay. Reporter, did you assume the heat flow is constant?
You mean inside the plate?
Inside the disk, did you assume the heat flow throughout the disk?
When there is a dynamic motion, then I don't think it will be constant.
Okay. Opponent, do you agree?
Yeah, it's not saying this.
Okay, cool. I agree. What about the heat flow from the heat source to the disk?
When we have a constant heat and it is not fluctuating much, then and the environmental parameters are approximately the same, and it will be approximately the same.
Okay, do you agree?
So would you rephrase the question?
With the heat flow between the heat source and the disk, and then the disk to the temperature, with those will be constant within themselves.
Inside the disk.
Like, I'll move on.
Okay.
Opponent, what did you mean by optimizing omega? Did you mean mass?
You mean optimizing omega theoretically?
Yes.
Well, I think that this question suggests us to optimize the steady motion, so it means that we have to suggest theoretically what omega it would be optimized. Okay. So yeah, in this case, so I have mentioned it.
Cool. Opponent, was there enough theory experimental comparison?
In their presentation.
In the presentation.
Well, actually, partly I believe that they have the Doppler theory and experimental comparison in qualitative mean. However, quantitatively it was weak. However, I believe that their theoretical model is imperfect, so that is why.
Why do some heating spots work better? The short sentence.
Because there actually has to be a balance between the heating spots, the actual the magnetic field, and its influence onto the magnet. And there has to be a balance between all these actual things. Yeah.
Do you know the Curie point of your magnets?
We actually tested the magnetic field of the magnet with the temperature, and it doesn't change much. So we assume that the magnet doesn't get affected as much with the heat. Yes.
And could you? Oh, I don't have time. Thank you.
Thank you.
Thank you.
I'll just, it should be, yeah.
Hi, my name is Mansell. Today I will be reviewing problem number 12, Curie engine. So the problem we've gone over a couple of times already, but I would like to point out the optimization for steady motion and investigate the parameters affecting the rotation. So they started off with the definition of Curie point. I believe this was insufficient, but this was brought out a bit in the opposition and the discussion. They explained the magnetic force. I believe this was quite good, though there were other explanation of other forces and talks lacking from the whole explanation of the rotation. And so I believe because of that, the explanation of the rotation was insufficient. There was a lot missing and there wasn't much depth into what causes it and why it isn't always steady. And then the model, there was a model which is quite impressive, as everything in this problem is codependent amongst each other, which makes it quite difficult to model. Practically the experimental rig, I thought it was quite good and quite interesting, though there was a lack of explanation into what this was and how it fully worked. Disk parameters, I don't believe that they varied enough about the disk or explained how it worked, and the heat source parameters I thought were good. For opposition speech, practically the cooling was considered. I agree, this is quite an important effect. He said the model, the assumptions and errors and the Curie point were all strength. I believe that these were not so strength of the presentation, and the visualization, I agree this was good, though there were things lacking from the diagrams, like the talks affecting it. The quantitative explanation, I believe, I agree that this was lacking, and I believe this relates to the visualization. The thermal efficiency, I agree that this is relevant, though I don't think it is the biggest point. The lack of quantitative explanation, I also agree with, sorry, that's said twice, the parameters in the heating area. With the vertical rotation, they don't really go into this, and the theoretical optimization. So the points that are discussed. So the heating source, they discussed how this changes more than the Curie point and the paramagnetic. I agree that it goes from ferromagnetic to paramagnetic, but there wasn't an explanation on why this causes a rotation and why this causes a decrease in magnetic force. Then they discussed the friction. I agree it might not have been significant for the disk sizes they tested, but I think that was a lack of experimentation and a lack of explanation of what this was in the presentation. Optimization. I agree that they didn't achieve optimization as they did not vary enough parameters and did not test everything with everything, as the problem is codependent and everything in the problem affects how it works. So you have to test everything with everything. And I think it was a significant point that could have had a bit more transferred on. They talked about the holes in the disc and the difference in heat conductance and the thermal conductivity. I agree that it can also change the heat flow within the disc and out of the disc and to the disc. They talked about the disc size change a bit more and how the magnetic field changes and the effect of change and the changing multiple parameters. And I agree with the opponent that they were changing multiple parameters at once and that this wasn't tested or modeled. So points missed. I think they missed what other talks were acting, like the electromagnetic drag and the torque from the friction. And I believe that this should have been brought up in the discussion, how this could have affected the rotation. I believe this connects as to why it was inconsistent motion. There was also a lack of discussion about the lack of magnetic parameters that were varied. They didn't change anything about the magnet, and I think this is crucial to the problem, as it states in the problem the magnet must be used. They didn't talk about the experimental to theory comparison and the others as well.
Okay, so firstly, the reporter would like to thank the opponent and the reviewer for such a fruitful debate, and we would like to go on to our concluding remarks. So firstly, about the magnetization saturation that is brought up by the opponent, we talked about how the magnetic saturation can actually be used to find the tendency, although it is not the absolute value of the actual magnetic moment of the disk. And our experimental observations show that the engine actually moves under the Curie point. And we explained from our discussion with the opponent that the reported things, it exceeds the Curie point because the magnetic accessibility is very small in a paramagnetic material. Therefore, the torque induced will not be large enough to cause the motion of the disk. That is why we actually observed the most parts of our rotation would be under or just slightly over the Curie point. And as the opponent suggested, there would be a huge drop in the magnetization when it is when it's just approaching the Curie point. We can see here, when it's not actually over, but it is near the Curie point, our actual rotation is actually smoother because there's a bigger magnetization, a difference so it will cause a better torque to actually let it rotate. And then also the reviewer asked about, is our magnet constant under the heat? And so actually measuring the magnetic field under the heat source, we can see that it stays a constant magnetic field in our experimental range of time. And then finally, so this is the graph about the saturation magnetization. So I want to explain once again here. So we think that in our experiments, when the actual temperature of the clay is around this section, it actually rotates better because there is a sufficient amount of magnetization change that will cause the torque of the actual nickel disk. And that is why we don't think when it actually goes over the Curie point, it will rotate better. Thank you.
Thank you. Question from the juror.
So to the report, so you showed us some of the formulas for magnetization and torque and so on. Have you performed any calculation and then compared them to experiments in any respect? Can you show any graph with your experiment and theory line?
Okay, so the problem from this
Can you show that or can you not show that?
no, because there is a factor here, the magnetic accessibility, that we don't know. Yes.
I think one question to the reporter. So can you show slide number 20 again?
Slide
20, yes, 20. So here you have graphical efficiency. So
yes.
How do you define this efficiency?
Efficiency is divided as the
Okay.
yes, yeah.
And
I have a question for you. So is it possible that you have rotation of the disk if the temperature, heating temperature is above the Curie temperature? Yes or no?
Yes.
If you have temperature below the Curie temperature?
Not too far below.
Yes or no?
Yes.
Okay, and what is then I will continue with the point. What is the difference? What is the difference if the temperature is above the Curie temperature and below it? And is there a difference?
The theoretical model to explain it should be different because the different law is applying to the ferromagnetic region and the ferromagnetic region. And yes, and
So to the report. So you mentioned you didn't show some graph. I guess you measured an angle of you measured some point on the disk as it rotates.
Yes.
Yes. And then from that you calculate your angular velocity. So
Yes.
how did you calculate your angular velocity?
So we use tracker to track the point on the graph, and then our frame is 0.33 seconds, and then we calculated the angle change over the time it used to calculate angular velocity.
So in just a short follow-up to that. So how these angular measurements, how reproducible were they?
So at first, on one situation, we did the actual experiment 3 times, and then found out that the rotation angle varies about 10 degrees each rotation, so it is not that much. So we actually only conducted one trial for every other case.
Thank you.
So their component, do you think that eddy currents are important here?
in these cases, well, I have not calculated appropriately, but I believe that it is not as much as important as the other parameters.
I believe that it is not the most important effect, but I believe it is an effect that could affect the inconsistent motion. So I believe it is something that should have been discussed.
Okay, I'll expand on it. So because we heat the plate and the actual domains get realigned, so there would be no significant, I believe that there would be no significant eddy current on the plate that will actually alter the rotation.
Yep. What was the material of the magnet that you used? What material was that? Was that like your standard bar magnet? Was that a neodymium magnet? Or what was the material?
Sorry, can I? Because I don't actually know the name.
Chair.
I think it's neodymium. Sorry, he doesn't know the English name.
And do you know the Curie point of neodymium?
So I showed, we don't know the Curie point, but we actually measured the magnetic field of the plate to actually ensure that it's constant. It will not be affected by the heat source.
Thank you.
You show the slide and you measure the magnetization, the magnetic field strength of the magnet, and the temperature changes. Where exactly did you measure that magnetic field strength?
Magnetic field strength. So we put the this is the magnet, and we have the disc here, and there is a diameter here, and we put the sensor above the point right here, and we fix it here. So actually measure the magnetic field, and we put it for the range of the time we did the experiments.
Right above the frame. Is that what you said?
Above the disc, so so this is here, put it above.
Any other short questions? Thank you.
Yes.